So at this point, I want to introduce the other kind of calorimetry. So previously we looked at constant volume calorimetry. So if you remember a little about this, right? This was done under closed system, sealed, right? We burned something inside that and we looked at the temperature change of the surroundings. So there we keep the volume constant, by, preventing it from changing. Now, what we didn't talk about there is that when that happens, typically pressure builds up within that calorimeter, right? This is why it has to be a sealed metal container, right? So as you burn that material, that combust it, it's going to produce gases, carbon dioxide, etc. Right? And so pressure is going to build up. Now, in this other kind of calorimetry, we're going to be doing it under conditions of constant pressure. So what this really means is that we're going to do them open to the atmosphere. So our pressure is going to be atmospheric pressure. So these reactions are done at constant pressure, meaning atmospheric pressure. Now, again, as most reactions that we do, we also have constant volume. Now, this is not because that we try to make the volume constant. It's just that we're looking at reactions where we don't produce lots of gases, and so we don't have a volume change, right? If we're working with a solution and I do a reaction, the volume of that solution doesn't change over the course of the reaction. So volume also is constant in almost all of these that we look at. But the key is the constant pressure, right? And this allows us to measure the enthalpy of the reaction, because remember, at constant pressure, the Q, which we measure directly, is equal to the enthalpy change. Okay. So the typical type of reaction we're going to look at is aqueous reaction. So we're going to look at reactions as we looked at the previous chapters ago, chapters 4 and 5. We're going to look at some of these classic aqueous reactions, right, where we're doing things in solution. So this means we're going to have to remember things like working with molarity a lot, and how to calculate moles when we have molarity and volume, right? So we're going to reintroduce some of these ideas or remind ourselves of some of these ideas. This is classically also called coffee cup calorimetry, right? Because oftentimes we'll do it in styrofoam coffee cups. These provide a very inexpensive, relatively well-insulated material. Typically we do it in a couple coffee cups so that we have one where the solution is and one that provides an extra layer of insulation. Sometimes we'll cover the reaction to even make it a little better, and oftentimes we don't really even cover it, right? We're not typically dealing with things that have huge amounts of energy changes so that we have to worry about a lot of heat escaping through the opening in the cups. And then we typically just have something to measure the temperature change, just like we had in the constant, the bomb calorimeter. And we might have something where it allows us to stir the reaction. So let's look at one of these reactions and we'll go through sort of some of the ideas as we look at it. So here's our chemical equation that we're going to use, and we're going to react 50 mils of a 0.1 molar silver nitrate solution with 50 mils of a 0.1 molar hydrochloric acid. And we see that the temperature rises from 23.4 to 24.21. And we want to calculate the enthalpy of reaction. Now, just like we saw in our previous, for a lot of these calorimetry problems, what we're really interested in is the delta H, the enthalpy per mole of something. So in this case, per mole of silver nitrate. So let's do a couple things in the beginning. So first of all, let's look at delta T. So delta T is going to be our final, right? 24.21 minus 23.4. so we plug that into our calculator, 24.21 minus 23.4, we have 0.81 degrees. Is our temperature change. Now, we're going to anticipate here, because we want to know how many moles, we want to do this per mole of silver nitrate, we're going to need to know how many moles of silver nitrate we have. So, in order to do that, right, we have to be able to calculate moles. So, remember, when we're dealing with solutions, typically we're going to get moles by doing the molarity times the volume in liters, right? So remember, molarity is moles per liter. If we times it by the volume in liters, we're going to get our moles. Okay, so what do we know? Well, we know that the molarity of our silver nitrate, right, is 0.1. We know the volume is 50 milliliters, right? 50 milliliters, right? We have 1,000 milliliters per liter, or 10 to the third milliliters, depending on whatever conversion, however we want to write the conversion. But we have 1,000 milliliters per liter, so that means I have 0.0500 liters. So my moles here are going to be 5.00, notice maintain the three significant figures, times 10 to the negative third moles of silver nitrate. Okay, so that's going to come in handy later. Okay, so now that we have these two numbers, we can start going back to calculating our Q. Now, unlike constant pressure, constant volume calorimetry, for constant pressure, we're going to use this equation for Q, right? So, because we're going to be using various amounts, of materials, various amounts of water in our solutions, right? We want to have a mass for our surroundings. And so we're going to use our broader equation where we break apart the heat capacity into the mass and the specific heat. Now, a couple of things that you'll find when you look at these problems. When we have Q of the surroundings, we will often refer to that for calorimetry as Q of the solution, because remember here, the system is very narrow. It is simply the molecules of silver nitrate that are interacting, the silver nitrate materials that are reacting with the HCl. So in this case, since we've got aqueous, it's silver ions, nitrate ions, interacting with hydrogen ions and chloride ions, right? So it's just those materials, those ions, that are reacting with each other. That's the system. Everything else, the water it's dissolved in, the styrofoam cup, right? That is all the surroundings. Now, we kind of ignore the styrofoam cup because it doesn't have a lot of mass, and frankly, most of the heat stays confined to the water, right? Because one reason that water is good for this is it has a pretty high heat capacity, right? So the water is going to absorb most of that heat. So really, we can focus on the water as our surroundings. Therefore, we just call that the solution. So when you see this sort of Q of solution, when you see the mass of solution, etc. In our solution, it's almost always equivalent to water, right? And so as it says in the problem here, use 1.00 grams per milliliter as the density and 4.184 joules per gram degree Celsius as the specific heat of the solution. Now notice that's the specific heat of water. Okay. Now, we have our equation, Q equals mass times specific heat times delta T. Well, we have the specific heat, we have the delta T. We need the mass of solution. Okay, well, we don't have a mass of solution. How do we do this? Well, what is the solution here? Well, the solution is the 50 milliliters of silver nitrate plus the 50 milliliters of HCl. That's what's in my cup, right? I have 100 milliliters of solution here. So my solution is 100 milliliters, right? The 50 milliliters and the 50 milliliters here. Now, I need this into a mass, right? Well, how do we get it from volume to mass? That's where the density comes in. So if I have 100 milliliters times 1.00 grams per milliliter, that means I have 100 grams of solution. So this is my mass. So now I have what I need. I have 100 grams my specific heat, my change in temperature, my units cancel, mass, and so my Q here is equal to $338.6 joules. Now, so this is my Q of solution. Now, if we remember, the Q of reaction equals the negative Q of solution. So that means the Q of reaction equals negative 338.6 joules. And since enthalpy equals Q of reaction, that means the enthalpy of reaction must also equal negative 338.6 joules. Okay. Now, the last part, right, is that's how much is given off in this particular experiment. But we want to put it on per mole of silver nitrate. So my delta H of reaction per mole of silver nitrate equals negative 338.6 joules divided by 5.00 times 10 to the negative third moles of silver nitrate, and that's going to equal negative 6.8 Now, two significant figures here because of our temperature, right? So we're going to limit this to two significant figures times 10 to the fourth joules per mole of silver nitrate. Or if you wanted to write it, you could write it as, this would be equivalent to 68 kilojoules per mole. So either way, you could write it in terms of joules, and that's fine. 6,800 joules, or so 68,000 joules, or 68 kilojoules per mole of silver nitrate. So this is the idea of solving these calorimetry problems. And you could do this with any solutions. You know, when you do the lab, you'll have other ones when you go to the homework. But the key is you're always going to follow the same basic protocol. You're going to initially get the Q of the surroundings or the solution. You're then going to be able to get the Q of the reaction based on that by changing the sign. We're going to be able to know that this is equal to the enthalpy of reaction because of our equality here. And almost always, you're going to ultimately put this on a molar basis for something. So it's going to be per mole of something that you're reacting. And so you're going to have to calculate moles. Right? We are almost always going to have to calculate the mass using a density because we're using volumes, but our equation requires mass. So a lot of these key ideas are going to be in every problem that you do with constant pressure calorimetry. All right, so we're going to stop. I'm going to stop here, and next time we will look at some of other aspects of thermal chemistry and enthalpy, and maybe some different ways that we can get to the enthalpy values of reactions in the next section. So we're going to look at the couple topics at the end of the chapter.